All right, let's get started. The recording is officially recording. Um, yes, the last or the penultimate Friday of this course, depending on how you choose to count it. Welcome everyone. Welcome to this lecture. Um, thanks for making it through most of the summer. Um, before we get started, a handful of logistical things as usual. So, um, problem set 6 is out. It's due by the end of the semester, so that's Friday. That's 1 week from today. Um, it is entirely extra credit, so uh, it's worth the same as all the other problem sets, but it's just like it's not going to go in the denominator of the calculation. So it's worth up to 6% extra credit on your total grade. Uh, which saying it out loud seems like a lot, but I've already said it, so I'm not taking that back. Problem set 6. PA3 is also out. Um, it is due by July 31st, which is this upcoming Wednesday, which is also the day that the exam is being released. I would encourage you to get it done by then, if not sooner. The late deadline is in there as the following Monday, like the Monday after class ends, after the semester ends. I guess strictly speaking, if you have 5 late days remaining, you could use all 5 and turn it in on Monday. But please don't. Um, there's a leaderboard as always, right? So top 10 and top 3 times get some extra credit. Um, yeah. The final exam um, is going to be take home, so it's open note, open book. Uh, I'll release it on Wednesday morning. Strictly speaking, I'll probably release it on Tuesday night or something like that, but you'll have starting Wednesday to work on it. And you can sort of work on it at your own pace. You can download it whenever, and just turn it in by midnight on Friday. So 11:59 p.m. Eastern on Friday, August 2nd. Uh, and that'll be did I say mid? I meant final. That's the final exam. Um, it is, there's no time limit, no. So you can open it and close it as many times as you want. Like it's just a take home exam. Um, the reason for doing that is number one, this way, sort of whatever time zone you're in, whatever other like commitments you might have, internships and other stuff, you can kind of plan around that as you want. I don't expect it to take a full 3 days to do. I expect it to be something closer to like a 1.5 hour exam. Um, I am aiming for something similar in length and difficulty to the midterm, which I realized the midterm was a little bit uh, kind of long. Um, and so that's, now you've got more time to work on it. Um, but the idea is sort of similar. So you can expect there to be a similar like point system setup. So I don't exactly know how many points it's going to be yet, but it's going to be more than the number of points it's worth. So it's possible to get over 100% on the final, or alternatively, another way to think about it is it's possible to get 100 on the final without completing every problem. Um, Not that I encourage you to sort of cherry pick which problems you want to do. I suggest you attempt them all, but just know that there is a little bit of like buffer. Um, and so you can sort of help your grade that way as well. Um, yeah. Any sort of questions on logistics stuff before we start content? All right. If there's no questions, I will open up a whiteboard. Okay. All right. Can I say again what we have for bonus? So the overall, the extra credit opportunities, you've got write-ups for the projects. You've got, strictly speaking, I guess you could say there's extra credit on the midterm and on the final, because there's more points available than what they're worth. So if you like complete every problem, you get all the points for every problem, you get more than 100%. Um, Problem set 6, which is released and is due by the end of the semester, is entirely bonus. So it's all graph theory stuff. It's all about stuff that we've talked about the past week-ish, and are probably going to talk about today. But it's worth the same as the other problem sets, but it's entirely extra credit, so you can get up to 6% extra credit on your grade. And then in addition to the usual extra credit for a write-up for project 3, there's a timing leaderboard. So if you're in the top 3 or top 10 times in the course, you can get some more extra credit for that. And I believe those are all the extra credit opportunities available. Cool. Will I be able to check my grades for problem sets and PAs that haven't been entered yet? Yeah, so actually that's a really good point. I am working to get all of the uh um all of the grades from Gradescope moved over into Brightspace. When I say I'm working on it, what I mean is my TAs are working on it. That should happen. Everything like Brightspace should be fully up to date before the end of the weekend. Um, for your programming assignments, I don't anticipate like whatever grade you have in Gradescope is the grade you're getting, modulo any like late days that you might have used. Um, for the problem sets, the ones that have been graded, that is also the case. Like the grades are final. Um, for the problem sets that haven't been graded yet, we're working on grading them and getting them in. Um, so right now, Gradescope is kind of a ground truth, except for the fact that it doesn't account for late days. So, but it'll tell you like how late you submitted an assignment, so you can sort of try to back calculate and figure out the late days that way. My TAs will get will get everything sort of accounted for and uploaded into Brightspace, or transferred into Brightspace before the end of the weekend. So you should have a good sense of like how you're doing in the class by then. Um, which also reminds me, the last day to submit regrade requests for the midterm is today. There haven't been any new regrade requests submitted in a little while, so I'm kind of hoping that there aren't any more. But if you have a regrade request, please make sure to submit it before the end of the day today. Um, that way we can get those grades into Brightspace as well. Okay, good questions. Any other questions? Okay, if there are none, let's get started. So maybe it's worth me spending like a minute going over what to expect on the final. I don't have a ton to say about this, but I feel like this is the sort of thing that people tend to care about for some reason. So um, final, there we go. Okay, okay. So similar in length to the midterm. Expect it to be uh, something on the order of like 60 to 65 points. It's only going to be worth 50 points. So extra credit is available if you choose to go for it. The it is going to be cumulative. So it's going to cover stuff from before the midterm. Like it's going to recover stuff that was on the midterm as well as new things from that we've covered since the midterm. Um, and a tentative list of topics include the following. You can expect there to be, maybe I'll write this actually. So topics. You can expect there to be roughly one question per topic. Um, so we've got linked lists, stacks and queues, right? This is sort of stuff that we talked about way at the beginning of the semester. We've got AVL trees, or I'm going to say like binary search trees. And in particular, this time around, I would focus on like AVL trees. So like self-balancing binary trees and stuff like that. You can expect there to be stuff about hashing. So this is like hash maps, collision, resolution, and applications. So by applications, I mean like if you have an like basically being able to identify when you might be able to use hashing or when you might be able to use a hash map to speed up another algorithm. And then graph stuff. So for graph theory, we'll probably, I mean, maybe I'll say like graph basics. So this is things like, you know, definitions, identifying, sort of like labeling part. I don't know, like knowing basic things about graphs. This is sort of like the very first lecture. Um, uh, BFS and DFS. Uh, and maybe I'll lump shortest path into here. Shortest path algos, and then MSTs. So this is minimum spanning trees. Maybe it's worth writing this out. I don't know. So this is a list of topics. 1, 2, 3, 4, 5, 6. It is possible that some of these get split into more than one question and some of these get merged. So for example, like graph basics might get merged with one of these two. Hashing might get split into more than one question. But you can sort of expect, broadly speaking, one thing about each of these. Yeah, so that's a list of topics. For studying, uh, I would recommend looking at the lectures and lecture notes, insofar as they're available. I'd recommend looking over your problem sets. And I would recommend looking at the CLRS textbook. These three resources should probably do a pretty good job of getting you prepared for the exam. And of course, I do highly encourage you to study together. As I said for the midterm, I don't know if there's a class group chat. I don't need to know if there's a class group chat as long as nothing untoward happens. But you know, feel free to discuss problems with each other and stuff like that. Before the exam, sorry. Feel free to discuss problems before the exam. Don't talk about the, I mean, yeah, I don't, okay. Maybe I shouldn't have said that. Anyway, yeah, studying. Please do so. Uh, Okay. Any like high level questions about the exam? Um, I don't have uh I don't think I have like valuable practice exams to send you just because we have deviated at this point from past semesters enough that I don't uh yeah. But like I said, these sort of these three sources tend to be like in particular the problems on the problem sets and the problems in the textbook tend to be sources of inspiration when I'm writing problems for the exam. And so it's sort of like if you have a good handle on the stuff from here, there's a reasonable chance that you will find yourself being at least somewhat familiar with what you see on the exam. And then of course lectures. Lectures are cool. Any questions before we do content? Before we do like computer science? I guess technically this is content. The max score for the final. So it isn't finalized yet, but it's probably going to be something on the order of 60 to 65 points. And it's going to be worth 60. It's going to be worth 50 points. So um, depending on where in this range we land, you're going to be able to get something like 20 20 to 30% extra credit. Any other questions? Will it be the same format? Yeah. So sorry. Uh, same format in the sense of like it's it's going to be like a booklet with a bunch of questions and you write your answers on a separate sheet of paper or like on a tablet or something and then sort of scan and upload them into Gradescope. Not the same format in the sense that it's not timed. So there's no like for the midterm, once you opened the Gradescope page, it gave you like 75 minutes before you had to submit. That's not going to be the case here. So you can sort of open it whenever you want. You can like come back to it and do whatever. So it is going to be actually maybe this is worth writing down. Um, Take home. I mean, insofar as take home means anything for an online class, but I'm going to call it take home. Open book, open note. So feel free to use whatever sort of offline resources you have available to you. Of course, being a take home exam doesn't mean that you should share answers with your friends or Google things or use ChatGPT or anything of that nature. Um, if you are caught doing that, the consequences will be dire. Let's say that. Maybe that sounds vaguely threatening enough. But in particular, like at the very least, a zero on the final, probably failing the class. So don't do that. I promise it's not worth it. Especially because you get access to any notes that you've taken, you get access to the textbook. So just don't do that. All right. Um, it will be designed to be something on the order of 60 to 90 minutes, but again, you can take however long you want. There's no time limit. Any other questions? Yes, there's no time limit. So, I mean, strictly speaking, the time limit is something on the order of like 72 hours because you could start it Wednesday as soon as it's released and then keep working on it until the end of the day Friday. But don't spend 72 hours on this. It's not worth it. Yeah, so you sort of just like work on it at your own pace, submit it when you're done. Any other questions? All right, let's get started with graph. All right, I'm gonna write graph, maybe graphs. Um, okay, so on Wednesday's lecture, we talked about spanning trees, and in particular, minimum, or I guess we talked about spanning graphs and minimal spanning graphs, and the fact that the minimal spanning graph is always going to be a tree. Um, we talked about uh, the idea of greedy. Maybe I should write this. Okay, so we talked about spanning graphs, minimal spanning trees. We talked about greedy algorithms. I mentioned the word matroid. This is important to me. Um, and then we talked about I believe we went over Prim's algorithm. I sort of gave you a pointer to Kruskal's algorithm. Now, what I meant to do yesterday, or in lieu of yesterday's lecture, is record a video of me attempting to implement these two algorithms um, live on camera. I did not end up doing that, unfortunately. So I'll do that and release it over the weekend, just so you have some sort of, I don't know, something. But I figured today maybe we can spend a little bit of time kind of walking through Kruskal's algorithm. And then depending on how much time there's left in class, I want to start talking about strongly connected components um, and this thing called Tarjan's algorithm. In particular, that is probably going to be somehow useful for the sixth problem set. So something to look forward to. I guess before we start, were there any like confusions or like things that I can help clear up about Prim's algorithm? Maybe for a quick refresher, uh, Prim's algorithm works as follows. You pick an arbitrary source vertex, and then you grow the tree by adding sort of min distance vertices, right? So if you think about having like a graph, you pick some starting vertex here, and then maybe you've got a bunch of other vertices like that. You sort of you proceed greedily. So you pick um, whatever vertex is closest to this one. So maybe that's this, right? You add uh, this edge, and now you find whatever vertex is closest to any of these. So that's this one. And then whatever's closest to any of these three. So maybe that's this one. And then whatever's close, so you sort of just you proceed in order of adding edges between uh, whatever vertex hasn't been connected yet to whatever's closest to everything else. And so this is an example of a spanning tree that you might get out of this graph. Um, this is with Prim's algorithm. Remember, spanning trees are not unique. Minimal spanning trees are not necessarily unique. So if we picked a different starting vertex, we might get a different set of edges. And maybe it's a good exercise to think about why that's the case. But that's Prim's algorithm. Um, so maybe we can think about the complexity of this, right? maybe we can start by thinking about like how we might actually go about implementing this. Um, so you have some like set of vertices. You want to kind of you want to grab them in order of their distance from the set that you've already picked. So maybe you want to use a priority queue where you insert vertices into the priority queue. You insert like neighbors into the priority queue and you add a new vertex. And you sort of keep track of like what the minimum distance is, and then you dequeue something from the priority queue. Um, and so you've got to visit each vertex, right? So there's at least a V. But then for each vertex, you've got an enqueue or a dequeue operation. And so that's going to be something that looks like log V, right? So the time complexity of this is going to be something like theta V log V. Um, I've kind of sped over this, but we did sort of talk about this on Wednesday. Are there any questions, any clarifications before we move on to Kruskals? All right, let's do it. Great. So Kruskal's algorithm, this one I'll go through a little bit slower. Um, okay, so I guess the pitch that I gave you about these two algorithms on Wednesday is that they're both greedy, but they're both sort of greedy in different senses, right? So Prim's algorithm is greedy when it thinks about vertices, so it sort of greedily adds vertices. Kruskal's algorithm thinks about the edges instead of the vertices. So I'll say maybe the tagline here is like thinks about edges, not vertices, right? So what does it mean to think about edges? Or what does it mean to sort of greedily think about edges? Well, if we're building a minimum spanning tree, we want the sum of the edge weights in the tree to be as small as possible. So doing something greedy means that we take the smallest edge first, right? And so we sort of do things in increasing order of edge weights. Um, maybe I can draw an example here again, right? I've got a bunch of points, and I'm going to start by picking the pair of points that are closest to each other, right? I don't start by picking a vertex anywhere, so there's no choice involved here, right? I just look at the edge that's sort of the smallest, and so I'll start by connecting these two vertices. And now, because I don't care about vertices, I'm not restricted to only looking at things that are like, I'm not restricted to only thinking about these two vertices, right? So I can just go back to picking whatever looks like the smallest edge. So I think that's going to be this one. And then whatever looks like the smallest edge is probably going to be this one, right? And then maybe this one, and then maybe this one, and then maybe this one, right? So I look at whatever the smallest edge is while making sure that I don't build a cycle on accident, right? So even if like let's say this edge were smaller, if I've already picked these two, I can't pick this one. So I ignore it, right? This doesn't qualify as one of the available edges. Um, so in pseudocode, uh, while so yeah, I mean we can just start by saying like while true, right? Uh, find smallest edge um, that, or find smallest edge between disconnected vertices and connect it um, when there are no more such edges, terminate. Right? This is kind of quote unquote pseudocode. Um, but we sort of keep finding the smallest edge, and at every step we make sure that the edge that we're about to add is not going to create a cycle. So that's what this disconnected vertices means, right? Because if the endpoints of the edge are already connected, either by an edge or by a sequence of edges, then inserting that new edge is going to create a cycle, and we don't have a tree anymore, right? And if you remember from Wednesday's lecture, the minimal spanning graph is always a tree, because if it weren't a tree, we could uh, we could delete one of the back edges, um, and it would still span, it would still be spanning, and it would have a lower weight. Minimal spanning graph with positive edge weights is always a tree, right? I guess I should clarify the thing about positive edge weights, right? So, um, how do we actually do this? Uh, there's sort of two components here, right? There's finding the smallest edge, and then there's knowing that two vertices are disconnected, right? Um, this is interesting, I think, to talk about. I guess I'm about to fall down a rabbit hole of explaining union find, but maybe that's okay. Maybe that's not the end of the world. So, okay, so first of all, smallest edge, this is very easy, right? So we start by sorting all the edges, right? Sort all edges by weight, right? This is E log E if we use a sensible sorting algorithm, right? We can like quick sort them or merge sort them or whatever, and it's going to be E log E. And now that we've got these sorted by weight, we can just sort of iterate through. Smallest edge just means like keep a pointer to the current smallest one that we haven't visited yet, and every time we visit an edge, increment that pointer. And if we add it, increment the pointer. If we notice that we can't add it because it would connect two things, increment the pointer anyways. And so you just sort of like always keep track of the smallest so far. Um, so that's easy, right? We can sort the edges by weight, and we can always get the smallest one. Now, how do we know when are two vertices connected? In particular, like when does an edge create a cycle, right? This is a question that we really want to answer. Um, when does an edge create a cycle? Because if it creates a cycle, then we can't add it. Um, the proxy for that, the way that we're going to think about this is knowing when the two endpoints of that edge are connected, right? Anyone have thoughts? How might you um, how might you determine this? Like if you were implementing this, if you were implementing Kruskals, how would you go about like knowing, right? So say you're implementing Kruskal, so you loop over the list of edges in increasing order of weights. You find an edge and you say, okay, am I allowed to add this to my tree or not? Right? You look at the endpoints of that edge. You say, okay, if I add this to the tree, is it going to create a cycle? In particular, are the two vertices on that edge connected? How do you tell? Anyone have thoughts? So one thing we can do, oh, check if the previous connected one is your next connections. Do you care to elaborate on that? Like the previous edge that you added? So a priori, the trouble is sort of like I might have two vertices here and two vertices here, right? And I might draw edges between them like this, right? So I might draw this one and this one, but the 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 trees that I have at any given point in time might not all be connected, right? Like it might be a forest. It might not just be one tree. And so I can't just say if two vertices have already been added, if there's already edges incident to both of those vertices, then you can't connect them. Because for example, we can still insert this edge, right? Even though it's incident to two vertices that have already been added, because those vertices have been added to sort of disjoint trees, right? And there's no like guarantee on the order in which we visit these, right? Like I might do these and then I might have um like some other edge that I draw here between two unrelated vertices, right? Or maybe I draw another edge like here first, right? And so now I need to know whether adding this edge is going to create a cycle, but it has nothing to do with any of the previous edges. I mean, it has nothing to do with the immediate previous edge that I've added, um, and it has nothing to do with whether these vertices have already been hit by an edge. So one thing that you can obviously do is add it no matter what, and then check to see if you've created a cycle, right? So one option is add the edge, detect a cycle. If there's a cycle, then delete the edge, right? This is technically correct, right? This will give you the correct output because we add the edge, we detect. How do we detect if there's a cycle in a graph? Anyone remember? Find operation? What do you mean by that? Using function find to find the edges. So given a graph, right? If I give you some sort of arbitrary, let's say for now it's undirected. Um, how can you go about determining whether or not there is a cycle? Like, say yes, there's a cycle here, or if I deleted this edge, say no, there's no cycle. What happens if you pick an arbitrary node, like so maybe start somewhere and run a DFS, right? If you run a DFS and there is a cycle, what's going to happen? What happens if we start, let's say here, and do a depth first search? Right, so we start here, we recurse onto this one, The stack now contains both of these. We recurse onto this one, so the stack now contains all three of these, right? Now we recurse onto this one, but now we notice that this is a vertex that's already on the stack, right? Or this is a vertex that is currently being processed. Like it hasn't finished yet. It's been discovered, but it hasn't finished yet. So if that ever happens, then we know that there's a path from a vertex back to itself. So we know that there's a cycle, right? So if we pick an arbitrary vertex, right? Pick an arbitrary vertex that's in the connected component containing the cycle, right? Which is fine. We can pick one of the vertices on that on the edge that we just added. We can run a depth first search, and if we ever run into the situation where one of the children or one of the like neighbors that we're trying to visit is actually already on the stack, is currently being visited, we know that we found a cycle. We can just terminate early. We can say, okay, stop everything, delete the edge, and pick a different edge, right? What's the time complexity of a depth first search? Anyone? Anyone remember? E plus B. Thank you. So a single depth first search is theta of E plus the number of vertices, right? Um, if we do this E times, right, once for each edge. So we sort all the edges first, right? So that's E log E. Plus we run a depth first search for each edge. That's going to be E squared plus EV, right? E squared is going to dominate E log E. This is going to give you something like E squared plus EV, right? This is fine. I mean, it's polynomial, um, but it's not great, right? Because we've got this quadratic term, and the number of edges itself in a dense graph, like E might look something like V squared, right? So this is going to be like theta V to the fourth, right? Which again, it's a polynomial, but it's like not a good polynomial, right? This four is pretty bad, right? So depth first search works, right? And a naive implementation of Kruskal's can use a depth first search, get the correct answer, and as long as your graph isn't too dense, um, and yeah, it's not going to be terrible. But it turns out there is a data structure that lets us do better, right? So um, there's a data structure called union find. Okay, so a union find. I don't know why I like staked out some space for it because I think I'm going to use more than this amount of space. So maybe um, maybe it's worth erasing this and just writing this down below. Actually, before I do that, okay, sorry, I'm all over the place, but I'll just say use a union find. And a union find lets you determine whether vertices are connected in roughly, I'm going to say, yeah, okay, yeah, fine, whatever, in roughly constant time. Okay. This is a lie. It's actually inverse Ackermann time. Um, but I don't I'm gonna say constant for now. It's so small that it's constant. Um, so if we use this magical thing called a union find, which to be clear, I haven't explained yet, and so maybe you shouldn't believe me that this is possible, but if you suspend your disbelief for just a moment, if we use a union find, then this e plus b becomes a constant, and so all we have to do is, something that looks like e log e, e log e to sort things, plus e times a constant to actually visit them. And so the overall complexity here is going to be e log e. Um, okay, let's talk about the union find data structure. So union find is something that supports um, two basic operations, right? I guess three operations. Yeah. So insert, union, and find. Okay. The idea is a union find maintains a list of disjoint sets, right? So you'll sometimes also see this called a disjoint set data structure. Okay. People know what the word disjoint means? I guess I've been using it. It basically they're completely separate, right? There's no like overlap between them, right? So if you've taken a discrete math class, you can also think of this as like it maintains a set of equivalence classes, right? Um, whatever that means. But okay, so uh, insert something into our union find. Unions two sets together, and find tells you which set something exists in, right? So the way we can use this is we start by inserting all of our vertices into their own set. Every time we add an edge, we so if I need a easy ways of switching colors. Okay, if I add an edge here, I union these two vertices together into the same set. If I add an edge here, I union these two vertices together into the same set, right? And I've got, sort of trivial one vertex sets around the other ones. If I now add an edge here, I union these two sets together, but in particular, that brings all of the vertices. Ooh, here we go. In particular, that brings all of the God, what am I doing? Okay, here we go. That brings all of the vertices with it, right? So unioning these two vertices together also unions together anything that they were connected to. So now I get a set that looks like this, right? And now if I'm ever trying to like add a new edge, all I do is I start by saying, okay, maybe I want to add an edge from here to here, right? So I just find the set that this vertex exists in, and I find the set that this vertex exists in, and I check to make sure that they're different sets, right? And as long as they're different sets, then they're not a priori connected. So the sets in this case represent connected components in my graph. Um, and so uh, I can I can do this, right? I can like make sure that they're not connected. Um, the way insert works is, or the maybe the implementation of a union find is I think pretty cool. But before I go into that, does Kruskal's algorithm make sense? So to sort of recap, we start by sorting all of the edges by their weight, and then we loop through this list of sorted edges to find like the smallest edge, then the next smallest, then the next smallest, and so on. Um, I guess there's now a step 1.5, right? Which is insert all vertices into a union find, right? So our time complexity now goes up to E log E plus V, right? Because now we have to do something for each vertex, but that's fine. We start by sorting all of the edges. We insert all vertices into their own sort of like singleton sets. And then we loop over all the edges, find the smallest one, connect its adjacent vertices, and union the sets associated to those vertices. If we ever try to add an edge where the two vertices, where the two endpoints are in the same set, we skip that and we move on to the next one. And we just do this until we're done with all the edges, right? And then the end result is a spanning tree, right? It's it's spanning necessarily because if it weren't, then there would be an edge that we could still connect to make it spanning. And it's necessarily a tree because at every step we've made sure that we've not added an edge that would make it not a tree, right? And it's minimal because of matroid. Like it's minimal because the greedy algorithm happens to be optimal in this particular case. And so modulo the details of how we do this union operation and how we do this find operation. Um, that is a correct algorithm, or that is like an algorithm that computes the thing that we care about, right? Are there any questions on that before I uh, talk about other stuff? Actually, it occurs to me, I'm not going to talk about union. I'll talk about union finds on Monday. Um, I didn't do an attendance poll yet. So your last attendance poll of the semester, explain how the algorithm ensures that a minimum spanning tree is produced. Yeah. So there's three aspects to this, right? So there's spanning, there's tree, and then there's the minimality condition, right? Um, so once the algorithm terminates, we're guaranteed that the graph that it produces is spanning, right? Spanning means that it touches every vertex. And we know it's spanning because if it weren't, like if there was a vertex that never got connected to any edge, then there would be an edge that we could add there, right? Um, so it must necessarily be spanning. I'm kind of lying about this. If the graph was connected, there would be an edge that we could add there, right? If the graph wasn't connected, then there is no spanning tree, but there's a spanning forest. Um, so we know that it touches every vertex that it can touch, right? Um, we also know that the resulting graph is a tree because the only way for it to not be a tree is to insert an edge that connects two connected vertices, right? To basically create a cycle. Um, and this union find stuff, or like the fact that we only find edges between disconnected vertices ensures that we never insert an edge that creates a cycle. And so it ensures that at every step we have a forest or a tree, right? So we know it's spanning, we know it's a tree. The minimality condition, maybe you shouldn't believe me just yet that the resulting tree will be minimal, right? That there's not like a smarter way to choose edges such that you get a smaller total sum. Um, but this happens to be the case, and the idea is like we're starting with the smallest edges first, and so if there was ever a smaller tree that we could have built, we would have built it. Like if there was a smaller tree we could have built, we would have built it by replacing one of the bigger edges with a smaller edge. But if we could replace a bigger edge with a smaller edge, then we would have just picked that smaller edge in the first place because we're going from smallest to biggest. That's the idea. That's the high level idea of the proof, right? But and so the like algorithm at the end of the day guarantees that we end up with a graph that spans, is a tree or a forest, and is minimal. And so in particular, it's a minimal spanning tree or a minimum spanning tree. Cool. Attendance poll. Send me a graph theory meme. That's your last attendance poll of the semester. Um, I will upload a live coding implementation of union fines and prims and Kruskals over the weekend, and we will talk about union fines on Monday. Actually, don't quote me on talking about union fines on Monday, but I will upload a video of the implementations over the weekend. Um, that's all I have. Any questions? Have a good weekend.